Hi everybody. So we've been talking about rotational motion and we introduced the idea of a tangential velocity, that along track velocity. So that gives us an idea that maybe we could do something more than just having something spinning on an axis. For example, the simplest thing we could think of would be a robot making a turn. And so there might be a central point that it's turning around, even though it's not necessarily attached to it. And then it makes that turn and then keeps going. So while it's turning, it's got a tangential velocity. As we saw, that tangential speed, the magnitude of it, might not be changing at all. We could be driving at the same speed as we go around the corner there. However, the direction is changing, so certainly there is some sort of acceleration. Well, according to Newton's second law, if there's an acceleration, there's also a force. That force is called the centripetal force, and don't get freaked out by that name. Centripetal literally means center directed. So any force that is directed towards the center of the turn is going to be a centripetal force. If I have a spacecraft in orbit around the Earth, gravity is acting towards the center, and so it is also a centripetal force. So we're going to look at a couple of cases with this, and in particular we're going to focus on this idea of a robot making a turn so that we can figure out a mathematical expression for this centripetal force. Let's get started. All right, so as we said, we're going to look at this idea of a robot turning, and you can see that it's kind of turning around this central point right there. So I can think about this as if this were the radius of my turn, that radius is going to be the same. So the robot here is moving at a constant speed, remember, of 0.15 meters per second. So you can think of that as being its tangential speed. As it makes the turn, has its velocity changed? And we've addressed this, but go ahead and jot down some ideas and tell me why or why not the velocity has changed. Okay, so remember the key here is that a velocity has both a magnitude and a direction. The magnitude in this case is staying the same, but certainly the direction is changing. You can see that I'm going in this direction here, and I'm going in this direction here, and then finally I'm going in this direction here. So my magnitude is the same, but my direction is changing. So this means then that there must be some kind of velocity, or it must be some kind of acceleration, because the velocity has changed, right? And as we said in the intro, if I have an acceleration, I must also have a force. And so this idea, this force that's acting this way, is what's causing that robot to turn. If you think about it, think about that string, the ball on the string. The string was pulling, there was tension. And so if this is my ball and this is my string, and I'm holding it right here, the ball, if I let go of it, remember, would just keep going this way. But the fact that there was a force, a tension, in this case, acting this way, caused its direction of its motion to change, to turn towards that center. And that's going to keep going because that tension is always center directed. So there is a force, and we're going to find out it's friction, but there is a force that's making this robot change its direction, and that force is directed towards the center, and that simply is what a centripetal force is. It's really not that complicated of a thing. Anything that's directed towards the center. Now you can see that if I have a force directed towards the center, that's going to cause my direction to change, just like that. Now I might also be speeding up along this path, because remember, I could have a tangential acceleration, which would be my along track acceleration. But even if that equals 0, I still, and let's say that this is a constant, I still must have a force here that's causing that change in direction. And so we'll put a little C there to show that it's a centripetal force. All right, so let's see if we can figure out what's going on. Now, we already know that it's got to be friction, and here's how we can think about that. So look at microtest 2. It says, suppose the robot was on a sheet of ice. Would it be able to make this turn? Just think about your everyday normal experience. Well, no, right? He could turn, but he's going to keep on going straight. from that. It doesn't matter which direction he's oriented, and this is going to happen in space as well. You may turn your spacecraft this way, but you're not going to change your direction. So this is why, you know, you see Star Wars and things like that, where you've got the spacecraft flying basically like airplanes. Well, no, they wouldn't really do that. They would have to turn, fire engines, and then they could make that kind of change in direction. The whole reason why airplanes can do that kind of thing is because there's the force of the air resistance that's making them be able to make that turn. Okay, so in this case, if it were on a sheet of ice, then no, it wouldn't be able to make that turn and keep on going straight. So what's the difference between the robot moving on the floor of the lab and on a sheet of ice? We've talked about this before. Well, that's going to be friction, right? So the lab floor has more friction than the ice does. And so that's why I can easily make this turn, but I could not if I were on ice. All right, let's take a look on the next page. So let's imagine an extreme case. So we're back on the lab floor. And let's imagine a extreme case where the robot instantly turned its tires 90 degrees to the right. So my robot is moving this way. We're going to look kind of looking down on it. And it's moving this way. And then it instantly turns its wheels this way. Okay, what direction is the friction in this case? And this might be a little tricky, so pause the video, think about it, give it a good thought, and then let's see what you decide. Well, remember that friction always opposes the direction of motion. Just because I turn my wheels this way doesn't necessarily mean that I'm going to be moving this way initially, right? The instant I turn my wheels, let's give our red here, the instant I turn my wheels, the friction is actually going to be this way. Right? And that's going to mean that I'm going to want to slide here rather than roll. So I turn and I'm just going to keep sliding like that. And you know, you see this in cop movies and that sort of thing. They turn and the car skids and then keeps on going. So that's what's happening here. Now, as we say here, of course, the robot cannot instantaneously turn its wheels to the side and turn to the left with this. So, and if it did, and if there were enough friction, of course, they would just go rolling down. This is actually how you roll your car. If you make a turn too tight so that there's not enough friction to keep your back wheels or your inside wheels on the ground, then you're going to flip the car. And we'll work out how that's done later on. So think about this, though. The faster that the car is going, then the less angle we can turn the tires without sliding, because if I turn the tires 90 degrees, then that's going to make that friction directly back. However, what if, let me clear this one so that we can see what we're doing. What if I turn my wheels just a little bit? Now there is less friction acting backwards on me. And so that gives me a chance for my wheels to actually make me start making that turn with that. So the inertia of the car makes it want to go straight, and if the force of friction isn't high enough, then it's going to slide. So one of the more important things that we can figure out is what is the maximum speed at which our robot can turn? And that's something you're going to want to know in its design parameters as you're working it out, because obviously you don't want to make your robot go too fast when it's trying to turn, otherwise it's going to flip. It's also probably a good idea for yourself when you're riding in a car is to understand, you know, how fast can I make this turn without causing problems. All right, so we need to figure out a mathematical expression that will show how to figure out what that speed is. All right, so we're going to figure out the magnitude of this centripetal force. All right, so suppose the blue robot is moving on exactly the same path as the red robot shown previously. So let me redraw that so that we can see what it is. So here's my red robot, and then he went this way, and then he went this way. All right. So let's suppose that the blue robot is following exactly the same path. So it's here, and then it's here, and then finally it's here. Okay, so suppose though that the blue robot is moving slower than the red robot going into the turn. All right. So the red robot has a much faster tangential velocity, a much faster along track velocity than the blue robot does. So which one is going to make that turn the fastest? Which one is going to end up in this 90-degree position fastest? Make your choice. Circle it in the book. Well, it's going to be the red robot, right? Simply because he's moving faster. So if I've got two robots and they're moving it along the same path, the same basic curve, if you want to think of it that way, and the red robot's moving faster, well, then he's going to finish his turn before the blue robot is. Okay, so given that then, which robot must be feeling a larger centripetal force? That one's a little tricky. Maybe think about it. Remember that it is the centripetal force that's making it turn, right? So that means there must be a greater force pulling in on the red one in order to make that turn. So the red robot must be experiencing a larger centripetal force. Let's pause and think about that for a minute. So the blue robot is not having to work against that centripetal force quite so strongly, because it's moving at a slower speed. And you can think about that yourself, right? If you're driving in your car and you're making that turn and you do it slowly, you don't feel any force acting on your body. And we're going to talk about the fact that you may feel like you're being pushed to the outside of the turn, and you're not actually, but that's for next time. Okay, all right, so given that this is true then, how is the relationship between the centripetal force and the turn speed? Are they directly proportional or are they inversely proportional? Well, they're going to be directly proportional, right? Because the red robot is making a faster turn and it feels a greater centripetal force. Right? So they must be directly proportional. So we know that our turn speed is going to have to be in the numerator of any equation that we come up with. All right. Now, which robot then is going to require more friction to keep from flipping over or sliding, right? So the force of friction must be equal in magnitude and opposite in direction from the centripetal force. So I must have a force of friction then, in this case, that's going this way. Otherwise, I'm going to skid. Whereas this one, they're balanced. And so a perfect turn is when the frictional force exactly balances that centripetal force. If the frictional force is too great, well, then I might flip my car. If it's not enough, then I'm going to skid, and I'm not going to be able to make that turn as quickly. So which requires more friction? Well, that red robot's going to require more friction. So we're building up the pieces here that we need to be able to describe what this centripetal force is doing. Okay, let's look on the next page. So remember, when we're developing an equation, we always vary only one thing at a time, always just one thing. And so now we're going to have our robots moving at the same speed. Okay, so our robots are both going to move the same speed. Got that right here. But the blue robot is going to have a larger turn radius than this. And let's see what we mean by turn radius. So you see that both of these robots are turning around that point. Let me lower that just a little bit so it's in line. Right there. And you can see that because that radius, that distance from this center point to here is the same for the robot everywhere here. And so that's its turn radius. Now the blue robot, on the other hand, still has a constant radius, and then eventually it'll get up here. We haven't drawn that, but it's got a larger turn radius. So the turn radius is the length, it is the distance away from the center of its turn. And no, there's not anything really here at that point that's making it turn, unless you've got some sort of Batmobile that you've launched out an anchor and you're spinning around that anchor or something like that, which, by the way, what that does is just increase your tension. It gives you an extra tension, so it gives you a little extra force other than just friction. So this, for the red robot, this is its turn radius. So the blue robot has a greater turn radius than the red robot. All right, so which robot then will make the 90-degree turn the fastest? Now they're moving at the same speed, so the tangential velocity for blue is equal to the tangential velocity for red. They're moving at exactly the same speed along the track. which one is going to complete that turn the fastest? Well, it's going to be the red because he's got less distance that he has to go. Does that make sense? So he's going this way, whereas the blue has to travel a lot further. And if you think about just the circumference of a circle, and this is only 1/4 of it, but if you think about the circumference of it, the blue robot has a much larger circumference. If it's moving at the same speed, well, then it's going to take him longer to do that. So the red robot is going to make that turn the fastest. Okay, so both robots are turning the same amount. So which one then must feel a larger centripetal force? And let's stop and think about this. Remember, the centripetal force is what is making it turn. The more centripetal force I have, the more turn I'm going to get. That's how you really want to think about it. Without that centripetal force, those robots are just going to keep going straight. All right, so which one has the larger centripetal force in this case? Since it's making more turn with the red robot than it is with the blue robot, there must be more centripetal force. Okay? So what is the relationship then between the centripetal force and the turn radius? Be very careful about this. Think about it. Don't just look at what we've circled here. So if I have a larger turn radius, do I have a larger centripetal force or do I have a smaller centripetal force? I must have a smaller centripetal force, so therefore they are inversely proportional. So you see that the blue robot has a larger turn radius, but it has less centripetal force. It's not making that turn as quickly. Okay, so here again, which requires more friction to keep from flipping over. If it's going to make that turn tight, that's what we call a tight turn, then it's going to need more friction. Otherwise, it's either going to flip or it's going to skid. So we want to have that balanced. All right. So we've got two pieces here that we've talked about so far. If they're moving at the same turn radius, then the centripetal force is directly proportional to its tangential velocity, its velocity around the curve. On the other hand, if I'm moving at the same tangential velocity and I have a larger turn radius, then that's going to be less centripetal force. I'm going to get less of a turn on there. And you can, again, think about it. The force is not acting as strongly on this, and that's why its direction isn't changing, because all that centripetal force is doing is changing the direction. It's not changing the speed at all. All right, let's look at the next piece. So we've got one more physical quantity that we need to look at, and that's the mass. All right, suppose we have the two robots are moving on exactly the same path. So my red robot is here, and then it's here, and then it's here. And then we're going to have the blue robot move on exactly that same path. So it's here, and then it's here, and then it is here. And furthermore, now we're going to have them have the same tangential velocity. So they've got the same velocity around the track. All right. The difference now is we are going to say that the red robot has a much greater mass than the blue robot. So the mass of the red robot is greater than the mass of the blue robot. Okay. So both robots complete the turn in exactly the same amount of time because they're moving at the same velocity and they've got the same turn radius. And so if you think about just if it were on a string, they would both have to reach there at exactly the same time. So now think about the friction. Which is going to require more friction to keep it from flipping over? The heavy robot here with lots of mass that's moving around the curve, or the lighter robot here? And if you want to think about that, think about a smart car versus a truck, right? Which one is going to require more force, more centripetal force, more friction to keep it from flipping over? Well, the heavier mass, right? If you think about it, that's just inertia. I've got this big heavy mass moving forward. If I try to turn it, I've got more inertia trying to keep me going forward with the red robot than I do with the blue robot. Therefore, it's going to take more force to act against that robot, to act against that moment of inertia. So the red robot then is going to require more friction to keep from flipping over. And now we've said that in order to make this perfect turn so that I neither flip nor I skid, I need my centripetal force to be exactly equal to the frictional force. And so that means then the red robot is going to have the larger centripetal force on it. All right, so what's the relationship then between the centripetal force and the mass? Well, as the mass goes up, the centripetal force goes up because it requires more friction to keep it going. So they are directly proportional. All right, so now we've got everything that we need. We know that it must depend upon the mass, and we know it's directly proportional. We know it must depend upon the velocity, and it's directly proportional to that. And we know that it must depend upon the turn radius. I'll make that a capital R so we can see the difference. And we know it has to depend upon the turn radius, which is going to be inversely proportional. So pause the video and let's put together our equation here. And as we say here, traditionally we use the symbol FC, F sub C, for the centripetal force. Go ahead and assemble your equation. Did you do it? Really important that we have this technique. All right, well, you probably came up with something like this. We said that the centripetal force then was directly proportional to the mass, and it was directly proportional to the velocity, and it was inversely proportional to the turn radius. Okay? And right now I'm just looking at the magnitude of it, because if you think about it, the direction of the centripetal force is continuously changing. That's kind of the point. So we may start out this way, and then it's going to be this way, and then it's going to be this way, and so on and so on. So we're just going to be looking at the magnitude. So I've intentionally not drawn any vector symbols on here. We're just looking at the magnitudes. All right, so the other thing we need to think about then is it could be directly proportional, but it could be squared, it could be cubed, it could be linear. Most of the time what we've run into, it's been linear, right? And so we haven't had to worry about it. But remember that anytime I'm creating an equation or I'm looking at any kind of equation, I have to have it balance on both sides. So in this case, I've got a scalar, so that's fine. However, I need to have this so that its units balance out. All right. So how can I figure out what its units need to be? Well, it needs to be in newtons, and so we could look at the fundamental units for that. So take a look on the next page. And so what we're going to do is we're going to figure out the units of this. So I need any equation. If I'm going to use the force, I just need what are the units of force. All right. And maybe you already remember. You know that it's newtons, and you might remember what the fundamental units for newtons are, but let's pretend you don't. So any equation that I have for the force will give me those units. And of course, the most common one that we can think of is this, which holds if I have a constant mass. You could also do it with this, and you'll get exactly the same units as you must. So it doesn't matter though, because we're not actually solving a problem, so let's stay with the one that's going to be simplest. So what are the fundamental units then of the force? Pause the video and let's work it out. All right, well, I know that this is a kilogram, right? And I know that this is a meters per second squared. So my units here then should be kilogram meter per second squared. All right, now take a look at our centripetal force that we've proposed. So just to remind us, we decided it was mv over r. So what then are the fundamental units of that? Pause the video, work it out. It's not hard at all. So the mass is kilograms, my velocity is meters per second, and then I'm dividing out a meter here with a meter in the bottom. Well, that obviously doesn't work, does it? So I need to find something that will allow my units to work. So right now, no, this equation here cannot be correct because it does not have the correct units. So what we want you to do now, pause the video. We're going to play around. I want you to play around with squaring or cubing or taking the square root or whatever you need. I can't change that I've got to have an m and a v and a top and an r in the bottom. But I could, for example, square the mass, or I could square the radius, or I could raise the velocity to the third power. Figure out a way to make it so that my units of the centripetal force equation end up being kilogram meters per second squared. Pause the video, play play the game, and then come back and let's look at it. Have you found a solution? All right, so I've got kilogram right now. I've got kilogram meters per second times meters, right? And that's just going to give me kilograms per second. So I know that I'm going to need to have another meters, and I'm going to need to have another second. Do you see that that's what's missing? I've got kilograms per second here. So what's missing then is I need to multiply by meters in the top and seconds in the bottom. And that'll give me kilogram meters per second squared, which is what I want. Well, what physical quantity has units of meters per second? Well, that's going to be the velocity. So if I take my centripetal force, and we're going to rewrite it, then if I have mv squared over r, now my units work out. And let's double check that just to be sure. So I've got kilograms from the mass, I've got meters squared per second squared from the velocity, times meters. That's going to cancel out just one of the meters, and that's going to leave me with kilogram meters per second squared, which are the correct units for the force. So this then is my final equation for our centripetal force. And that's worth making a flipbook page for. So anytime I want to know what that force is, then I just take my mass times the velocity. Now remember that that's the tangential velocity, and so if you really want to put a t there, you can. We don't traditionally do that, but it's okay. You need to remember that that is my along track velocity as I'm making that turn. So then divide by the radius of the turn, which is this imaginary center point that gives me the same radius as it makes the turn. So that's the radius. So you can think of the radius of the turn as being kind of the tightness of the turn. The smaller the radius of the turn, the tighter the turn, and so the more centripetal force is going to be involved in making that turn because it's got to pull harder. And then, as we know from our robot, that means if I want to make a perfect turn, I don't want to skid and I don't want to flip, then I need to have exactly the same amount of friction as I have the centripetal force. And that's how we can figure out all of this. So finally, yes, our expression does have the correct units. All right, so now that we've introduced the concept of a centripetal force, what we're going to look at next time is we're going to explore some of its consequences, and that's why we call it understanding centripetal force. Centripetal force is confusing to a lot of people. You've probably heard of centrifugal force, but there's no such thing as a centrifugal force. That doesn't exist at all. What you're actually feeling is the centripetal force, and you maybe see, but wait a minute, Dr. K, when I make that turn, I feel like I'm being pushed to the outside. Well, you're not actually. But we're going to figure out how that works in our next video. We'll see you next time.